All right, so now for the cheating aspect of this. So in the last couple of videos, we looked at a few different algorithms. We saw the very first one ran in about big O of n squared. We were able to improve that thing down to a big O of n log n, which was a pretty big savings. But it's not quite at this kind of ultimate quest of trying to get all the way down to big O of n, which is absolutely the best we can do because it's going to take n readings just to get across this tape. So the way that we're actually able to get all the way down to that thing is by cheating. And the way that we're going to cheat is we are going to not use a single tape, but we're going to have a second tape. So definitely introducing some cheating aspects, but it gets us down to that big O of n, so that's kind of fun, but we'll see how it all pans out. So what I mean by a two-tape system is I'm going to have my initial tape where I'm going to paste this word into it. So again, the same word from before. I have 14 overall symbols, so 7 zeros and 7 ones. And underneath that thing, I'm going to have another tape. That tape is going to come with its own little head. So both tapes have their own head, and they can read and write and move independently. So that top one's going to do some stuff, and then the bottom one's going to do some stuff. And the way that we go about this is pretty cute. It does definitely feel like cheating because that is in fact what we're doing, but it at least leads us a little bit more into how you actually may implement this with some lists and arrays and things like that. So essentially what we've done here is we have our initial array and I've created another array underneath it. So what's going to happen is that as I begin reading this thing left to right, what I'm going to do is I'm going to X out those zeros, and then I'm going to leave a breadcrumb trail on the second tape. So I'm going to move across, so as that top tape is moving, that bottom tape is moving as well. So now what ends up happening is both of those are going to end up down here. So what ends up happening is that when that top one moves over and begins seeing that 1, the second tape is going to change direction and begin removing all of those X's. Essentially, this block of X's should then be the same length as that block of 1s. So if that top tape makes it all the way back to this blank at the exact same time that this bottom tape makes it to the blank, we know that the zeros and 1s are the same size. So it's this kind of convenient way that that bottom tape is essentially keeping a count of how many 1s do I need to go. So it's essentially being like, okay, I need to do that many 1s. So however many X's I have, that's how many 1s I need. So what's going to happen is that as this thing moves over, I'm going to X that one out, and then that thing's going to get blanked out. Then I'm going to X this one out, and then I'm going to delete that one, and then exit and delete, and then exit and delete, and then exit and delete, X and delete, X and delete, and hooray, our two tapes are now both staring at a blank, which is to say that I have in fact matched the zeros with the 1s and everything is great. So hooray! We definitely cheated, but this whole process actually runs in big O of n, which is really, really neat. I only had to go across that first tape once. I had to read all 14 symbols and everything was great. So we have this kind of nice hierarchy. We had this big O of n squared. It went down to this big O of n log n. And then eventually we got all the way down to just a nice linear time process. There are some pretty cute results that make connections to these multi-tape systems into a single tape. In that if you have something that runs in big O of some time, which we're going to say big O of t of n, if that's happening on a multi-tape machine, so what we just saw is that on a multi-tape Turing machine, we ended up running in big O of n. So my function t of n was just n. What this says is that there is an equivalent big O of n squared machine, which we actually saw before. We actually were kind of able to make our very first pass of this running in big O of n squared. So what this is telling me is that anytime you have something running in big O of t of n on a multi-tape machine, you can actually create a single tape machine that runs in big O of t of n squared. So if you get something that would run in big O of, let's say, log n on a multi-tape, the single tape version of it would then run in big O of log n squared, is how that's reading. So So it's kind of fun to play with these multi-tape ones. As I mentioned, they are introducing some cheating. They are an extension of some of these models of computation. They are worth mentioning because you can always take these multi-tape systems and then embed them into a single tape. You obviously realize that if you can do something super efficient with 2 tapes, you might not be able to be that efficient in a single tape system. But it's still kind of fun to play around with because you get a bunch of this kind of moving and shaking and all that kind of stuff. So throughout this notes set, I did make some comments about this world of Big O and things like that. If you go to the very beginning of this set of notes, I have a little bit more structure about what this whole process is all about, as well as some of the terms and notations and things that we're going to play with. So some of the very common ones that we're going to see are things like linear and quadratic and cubic, or just generally polynomial. We also get things like big O of log n and big O of n log n. Sometimes we'll nest some logs together, so you get big O of log n. All of these are very classic, fairly fast algorithms. They're all really nice. Once we jump into the crypto side of things, we're then going to see some pretty slow and terrible things. But that's going to be our hope, is that we want some things that maybe don't run fast because that's where the security is then going to come into play. So this is actually the official definition of what this big O is all about, is that you're going to have some function is big O of something if it's going to behave essentially the same as that other object, which is where things like you're going to have a 3n squared plus 2n. That's actually big O of n squared. All I'm doing is I'm just ripping off the largest term and I'm throwing away all the little constants. So that's why when I began dancing around on some of these machines, I didn't really care about all those little tiny nuances of, like, well, maybe we have to come back over one more time. Or maybe we have another pass, or these extra little blips on the edges of like, okay, I have to find the blank and then turn around. I didn't have to worry so much about all of those little nuances because big picture, that would still be big O of n squared or big O of n log n. Having all of those extra little things don't necessarily matter. So if I had to read across the tape 10,000 times, so I'd have, 10,000 n, that's still going to become big O of n. It's when you began nesting those things, which is where you started seeing the squaring operation come into play. So any amount of constant you can just shove in front of things and that doesn't affect stuff. It really begins to matter once you have this kind of nesting structure. Once you began seeing something that's going to have a dependence on something else and you get this kind of blocking structure take shape. That's where you started seeing things that were going to be big O of n squared on that one. And down here in the crazy one, this is where you started seeing this big O of n log n. Everything else can just happen as many times as we want to. So we'll chat a little bit more about that as we go through some things, but I wanted to kind of introduce it in this Turing machine world because you get this kind of nice exact knowledge of where things are going. I can actually count out exactly how many operations are going to take shape and then very quickly transition it back into this big O structure.